So here we go. We need to talk about the inverse of an exponential. We've spent time recapping the exponential function ideas that came out of Algebra 1. So the simplest exponential we can work with would be y equals b to the x, right? A is equal to 1, so we're left with just that most basic version of the curve. The inverse would be found by us switching x and y. So we'd arrive at the statement x equals b to the y. Now that's also going to be a function if we think about what the reflection of that exponential curve would look like. The way we like to see functions written is y equals and then some expression involving x. The way we do that here is to write y equals the log base b of x. So y equals the log base b of x. Now, this is the logarithmic form of that same exponential expression. It has to follow some rules, just like our exponentials did as functions. So when b is greater than 0 and b is not 1, that should sound a little familiar. More on that in a second. The log base b of x is equal to y. Now that's if and only if b to the y is equal to x, because that's where this expression came from. I've said it a couple times, but we'll put it in print. We read that expression as the log base b of x. Some things to keep in mind. That log, right, we'll call it y, but it's that expression, the log base b of x, is an exponent. Now, it's a very specific exponent. It's the exponent that you would put on b to get x. Now, that statement, that understanding is what we need to know in order to be able to work with logs in terms of evaluating and manipulating. So, going back to where this comes from and the idea underlying the need for logs, when we first wrote that expression, when we swapped x and y and we wrote x equals b to the y, that y is the same y as when we write it in its logarithmic form. The b, the base to our exponential function, is the same b that is the base in our logarithmic form. And in both cases, that b follows rules. It's not equal to 1, and it's got to be greater than 0. It's got to be a positive number. So since b's got to be a positive number, then b to the y is always going to also be a positive number. You can't take a positive number, multiply it by itself a bunch of times, and arrive at something negative. And since we're always going to get a positive number, then x must be positive, since b to the y was also equal to x. Now, that means that if x is always positive, the inverse there, well, it's only going to be defined for positive values. We won't have any definition to explain away a negative value for x. That makes that the domain of our logs as a function. Now, this also makes sense if we think back to what the range was for the most basic version of our exponentials. That range for an exponential was from 0 to infinity. Well, if you swap range with domain when you create the inverse, that same interval should apply. Now, the other tidbit about them being inverses. When we compose these functions, that's the f circle f inverse at x, f composed with f, that takes the input value and spits the input value right back out again after having passed through both of those functions. So that means that b to the log base b of a would also be equal to a, because a would be the input into the log and then the output after the exponential for any a greater than 0. And the log base b of b to the a would be equal to a, where a is the input value into the exponential and then ultimately the output value for the log. So how do we move between forms? Well, in order to move between logarithmic and exponential form, we need to take into account how we just defined a logarithmic expression. We defined x equals b to the y to also be able to be written as y equals the log base b of x. Well, if we take each of these pieces into account, that means that x is 81, b is 3, and y is 4. So if we just move those pieces around to fit into our logarithmic form, we get 4 equals the log base 3 of 81. This supports that idea that logs are exponents. We're asking ourselves, well, 3 to what power would get me 81? The answer is 4. Second example, 125 equals 5 to the third. I still refer back to that definition of the log. So x equals b to the y is also written as y equals the log base b of x. 125 is x, b is 5, and y is 3. Rewriting those pieces in the other places, 3 equals the log base 5 of 125. These are both the exponential and log form of the same statements. This is useful, especially for situations where we saw with exponentials, if we were trying to solve for time, which was always part of the exponent in some of those models, we didn't have a reliable means of getting there. Logs are the reliable means of getting there. So one more example. We want to rewrite 32 equals 2 to the 5th in log form. So x equals b to the y equals log base b of x. Again, we refer back to our definition. So that means that 32 equals 2 to the 5th can be rewritten as 5 equals the log base 2 of 32. Now, what if the exponent is missing? I want to evaluate that. So we have 3 examples here. The log base 3 of 27. I have to imagine that there's some x I'm trying to find. I want to know what the exponent is. That's really saying, well, 3 to what power gives me 27 if I rewrite it in exponential form? Well, 27 is really 3 cubed, so 3 to what power gives me 3 cubed? X would be 3. Log base 10 of 100. Well, just looking at it as it is, you'd say to yourself, well, 10 to what power gives me 100? That's the x we're searching for. Well, 100 can be rewritten as 10 squared. That means that x must be 2, because if 10 to the x equals 10 to the second, x is 2. Finally, the log base 8 of 128. Rewriting in an exponential form doesn't seem immediately useful. 8 to the x equals 128. Well, 128 is not a power of 8. So we have to find some common base to rewrite them. Well, since 8 is really 2 to the third and 128 is 2 to the 7th, then 2 to the 3x equals 2 to the 7th, which must mean 3x equals 7 or x equals 7 thirds. So that means that 8 to the 7 thirds power would be 128. One final example. If you're asked to evaluate the log base 9 of 243, well, that means that we're looking for some x value, that 9 to the x equals 243. 243 is not a power of 9. They are both powers of 3, though. So 3 squared to the x equals 3 to the 5th. That means that 2x must equal 5, and 5 over 2 is x. So that means that 9 to the 5 halves power would be equal to 243. Feel free to check that in your calculator.